Welcome to our help video on our valence shell electron pair repulsion theory or shape quiz. This is 6C10. Our very first problem, part 1, we are asked to answer some questions about tetrafluoroborate ion BF4-. Generally, when I see an ion, right away I want to realize that I don't catch myself later. I want to realize that this is ionic. So the strongest intermolecular force that it will exhibit is a fully charged ion. So we know number 6. It's smart to go ahead and circle answer A right away so that you don't get caught up in the shape and determining whether the shape is symmetrical or asymmetrical, which might lead you to thinking, is this polar or nonpolar, when it is actually fully charged. It's sometimes easy to forget that it's charged later. A full charge will pull this particular molecule. When it's around another full positive charge, it'll pull together strongly and form a salt. So I have answer A circled. That way I'll have less chance of missing it later when I go to analyze the shape of this molecule, because they're still going to want us to do the shape of this molecule. To do the shape, we have to determine how many electrons there are. We have boron. It has 3. We have 4 fluorines in Roman 7. They each have 7. That's 28. 3 and 28 is 31. Right away, when I see the number 31, I get a little nervous because that would mean we would have an odd number of electrons if we only had 31, which creates a whole different set of circumstances, because we've seen on all our molecules that things tend to like to have those pairs of electrons. Each orbital holds 2, so we like to have the orbitals filled in order to satisfy the octet, which is an even number, or duet, which is an even number rule. So 31 is not a good number to work with, but we don't have 31. This molecule's 1-. That means it has 1 extra electron on the molecule than we would normally expect. 31 and 1 is 32, so we have 32 electrons to work with. How do I know what the central atom is? A lot of these formulas give you away the central atom. A lot of times the first one listed is the central atom, especially when we have just 2 elements or 2 atoms in, or 2 types of atoms or 2 elements making up the molecule. Usually that lone one is the one that's in the center. Plus, it makes sense, too, because boron only has 3 electrons, so it's going to be able to make more bonds. It would like to make 5 if it could, but it only has 3 electrons, so it can only make 3 normal covalent bonds. In this molecule, though, we're going to see that it makes a type of covalent bond which really isn't all that normal. It'll make a coordinate or dative bond. Coordinate covalent or dative bond. So needing more bonds, we're putting boron in the middle. So we have boron in the middle. I like to use brackets right away and put the minus outside so I don't forget to do that. And we're looking for 32 electrons. So boron's in the middle, and we will surround it with 8. Now, when boron only has 3, it wouldn't make sense really to surround it with 8. But remember, if you follow the Lewis rules, it will eventually lead you to the correct drawing. So our Lewis rules, surround it with 8. And now we'll go ahead and attach the fluorines to it. Put a fluorine on each pair. And now we will surround the fluorines with 8. So we have boron in the middle. It has 8. We attached each of the fluorines where there were lone pairs. And now everything on this molecule is surrounded with 8 electrons. And that meets our 32 electrons. So we've got a good drawing here. So at this time, we could replace all shared pairs with a line and make it a Lewis structure. But there's something interesting that we wanted to talk about. Here we had boron. Boron only has 3 electrons when it starts. So it shares 1 with each of these 3 fluorons. Where does this other bond come from? How do we get the BF-? How does boron end up with 8? Well, it does not form what we would consider to be a regular covalent bond. What really happens here is we have a molecule that starts off as BF3. So we have a molecule right here, BF3. I'm just going to put a little line right here. Here is our initial molecule, BF3. Boron sharing one of its with fluorine. Fluorine sharing one back on all three of these sides. So these are three regular covalent bonds. But boron needs 8. And it is looking for a pair right here. What happens is, if we have F- floating around, here's fluorine that's picked up an electron from somewhere. It's the fluoride ion. If a fluoride ion gets near this BF3, this boron is going to try to share that pair of electrons on the F-, on the fluoride ion. In this case, boron is not offering any electrons into the covalent bond. So it's not a normal, ordinary, everyday, run-of-the-mill covalent bond. Instead, it's a special covalent bond where one of the atoms is supplying the electrons in the bond. So fluorine with its F-, this F- will end up sharing that pair with the boron. That is called a dative or coordinate covalent bond. Again, that's where one of the atoms doesn't offer any of the electrons. Both electrons are shared from one of the atoms to the other atom. A coordinate or dative bond. And that allows boron to end up with its 8, satisfying the octet rule. Ways you can recognize if a coordinate or dative bond is on the molecule is in this particular instance, where you have an atom that doesn't have enough electrons to make the number of bonds it needs to make to get 8. So if you see something with 8 that normally couldn't get 8, chances are it's a coordinate or coordinate covalent bond or dative bond. Another way to recognize it is something has 8 but is making more bonds than it normally needs to get 8. That means if it needs 2 bonds to get 8 and it's made 3 and still has 8, that means one of its bonds it's not getting electrons back. Coordinate, covalent, or dative bonding. But we have our F, 4-, our tetrafluoroborate ion, and now we are ready to analyze it. Well, wait, before we analyze it, look here. There seems to have been a little error in this original drawing. I'm glad we caught this before we went any further. There was an extra pair of electrons thrown in there. Got a little sloppy with putting the electrons in there. Now we have 32 electrons. The day has been saved. If you were wondering why was there a double bond between that boron and that fluorine, there wasn't. Sorry about that. I probably should redo the whole video and start from scratch, but we did catch it, so let's just press on and begin analyzing this molecule. So on this particular molecule, this is the one that we were talking about possibly being the dative bond, where this fluorine is offering the boron a pair of electrons without any paired back. Sometimes you'll see that bond not drawn as a line, but as an arrow. So if you see an arrow pointing from one atom to the other atom, they're trying to show you that that could potentially be a dative or is a dative or coordinate covalent bond. Sometimes students get confused with the arrow drawn there because they think you're trying to show a dipole. Remember, a dipole will have a little slash at the other end of the arrow, the side that's not on the pointer side, and that slash goes on the element that is going to be the one that is partial positive, with the arrow pointing at the one that's partial negative. Here, this isn't a dipole. Dipoles are drawn over the bond. They've just put a little tip on the arrow to show that it is a coordinate covalent bond. Fluorine's offering the pair to boron. Boron's not putting anything in. So that's what the arrow means. All right, let's take a look here at the shape of this. We're going to count the number of things around the boron. Things are steric number. Steric number are things where each pair counts as a thing, each pair of electrons that are not in bonds, lone pairs or unbonded pairs, unshared pairs, that counts as 1, and then atoms count as 1. So boron here has 4 atoms around it. There are no lone pairs, so our total things, or our steric number, is 4. We can now answer number 1, because when you have 4 things around the nucleus, or around the central atom, you are called tetrahedral family. You belong in the tetrahedral family. So we can circle letter C. tetrahedral family. The tetrahedral family, if we look down here, the tetrahedral family has three possible shapes. Tetrahedrals, the 4-0. Trigonal or trigonal pyramidals, 3-1. Angular or bent is 2-2. Let's go ahead and take a look at the shape. Well, it is a 4 atoms, no lone pairs. So we can put 4 here. We can put our 0 here. It is tetrahedral. So we have the 4-0. Again, that's tetrahedral. That makes our shape formula, AB4E0. So we can just kind of skip ahead to number 4 if we want. The AB4E0, here is our tetrahedral shape, letter D. We can circle that one. With tetrahedral, there really are not axial and equatorial atoms. They are spread evenly around the central atom. So we can look on our shape sheet to get the bond angles. We would see on our shape sheet, the 4-0, the bond angles are 109.5. 109.5 is our bond angle, so we have that circled. So that takes care of questions 3 and 4. We head to question 5. What is the symmetry when we are a 4-0? When we're a 4-0, we have 0 lone pairs, so we come out of here. When we have no lone pairs, that would be symmetrically shaped. But it's important to read here, no lone pairs and the same atoms surrounding the central atom. Both of those conditions must be met for it to be symmetrical. Because if you have different atoms around it, symmetrical means same. If you have different atoms surrounding the central atom, in other words, we've got a boron. If this was a fluorine, a hydrogen, and a hydrogen, it would then be asymmetrical. Those would be different atoms. But they are all the same atoms, symmetrical. So we can follow right through here, and if it was just an ordinary run-of-the-mill molecule, if it wasn't an ion, we would have a nonpolar molecule automatically. But we already circled the fact that it is ionic because it was charged. So we already have number 6 done, and that completes the questions on our first part 1, the tetrafluoroborate ion. Our next video we'll pick up with part 2, our next molecule we are drawing, SOCl2.